attained everything. So academic counseling is different from teaching. In academic counseling, your questions will be discussed by the teacher. But anyway, yeah, you together means our academic counselor as well as the learner will together they decide how to go about the these 2 hours which you will be interacting. Okay, sir. Thank you very much.
Okay, thank you, sir.
Please hand it over to you, sir. Thank you.
Thank you. Yes, good afternoon to all of you. Is it visible to all?
Yes, sir.
Is
Yes,
it
sir.
visible?
Yes, sir.
Yes,
Okay,
sir.
okay.
Yes, sir.
Okay, I have already sent you the PPT, which covers your first unit, that is your fundamental, which we covered in the previous class. Okay. Today we will discuss about the analysis of algorithm. Okay, this one. Okay, actually there are three types of analysis. That
ورونه وبخښئ هغوی خو لیفټ شول. زه یو پوښتنه کوم که تاسو معلومات لرئ، زه په لاست سیشن کې نه وم. دغه اساینمنټو په اړه استاد چې وغږېده دا د همدغه سمستر اول سمستر اساینمنټو موضوع ده چې تر اوسه اپلوډ شوی نه دی، که دویم سمستر لپاره دوی دغسې پلان لري؟
جنرال صاحب دوی داس خبره وکړه.
Dear learner, you have to, if you want to ask anything, you will have to speak in English or Hindi. If you know Hindi, then it's okay. Otherwise, you interact in English only.
now it's
Okay, sir.
visible.
Yes.
Actually, there is some network issues today.
Okay, sir. Okay, yes.
Okay, in the previous class, we have discussed about different types of analysis. That was your how an algorithm works. So in the previous class, we have discussed about different types of analysis. That was your from order of 1 to 2 to the power n. So there are three kinds of analysis. That is your worst case, average case, and best case. That we discussed earlier also. In worst case, the maximum type of the algorithm, an algorithm that takes the maximum time to complete, to execute. Actually, we will talk about only the time. We have a lot of space. but there is a requirement of time. So worst case is a maximum time, how much an algorithm takes. Case was your minimum time that algorithm takes to execute. As we have taken an example of your linear search. In the linear search, the best case complexity was your order of 1, that is the constant time. Because in linear search, in the constant time, in the order of 1 time,
Excuse me, sir.
element we will find out.
Sir, if you maximize the PPT, we can't see.
If it is not visible,
Visible, but it is small.
okay. Best case, okay. In binary search, when we find the element in the first position, that was the best case. It will take your order of 1 time. That is the best case. In worst case, if the element was present in the last position or in the second last position after the mid element, then that will take your maximum time. Then that time the total number of the maximum number of comparison will be your n. So the worst case was your order of n. And in average case, the element will be in the middle or after 1 and 2 greater than. Now we will talk about notations. Different types of notations use the one more present, that is your is it visible my PPT?
Yes, sir.
Okay. Okay, the notations. Okay, notations are used to measure, to check the analysis of the performance analysis of any algorithm. So there are total 5 notations are used. These notations are commonly used in performance analysis and to characterize the complexity of an algorithm. These are your big omega, theta, little o and little omega. These are your notations, asymptotic notations. These notations are called your asymptotic notations, which are used to represent the complexity of an algorithm. This describes the growth rate of an algorithm. That is called your asymptotic growth, which is the rate of growth in which the function grows. That is called growth rate of any functions in terms of the complexity. So growth rate is the complexity of the function or the amount of the resource it is taking to compute. So growth rate equal to, that will be your time plus memory. How much time it is taking to execute and how much space it takes. That will be called your growth rate. So mainly there are 3 asymptotic notations: omega, O and theta. Omega and further categorized in 2 notations, big O and small o, little o, that is also called little o. Next, big omega and little omega, and one more, that is your theta notation. So there are total 5 types of notations which are used to analyze the algorithm. To analyze that, these notations are called your asymptotic notations, and this analysis is called your asymptotic analysis of the algorithm. So our approach is totally based on the asymptotic complexity that is measured with these 5 notations. This means we have to try count the exact number of steps for a program and how that number grows with the size of the input sizes increases. As we discussed in previous class also, the time doesn't mean your clock time. It means the count of exact number of steps that a program takes and how that number grows with the size of the input to the program. That gives you the measure that will work for different operating systems. So asymptotic notation that is written in different types. Is it visible? I think it is not visible.
No, sir, this the black screen.
Yeah, there is a. I'm also. Wait a minute. Is it visible now?
No,
No,
not
sir.
sir.
But there is.
Yes,
Yes,
it
sir.
is.
Now is it visible? Okay. First one is your big O notation. Okay, big O notation. This always describes your maximum time. That is also called your worst case complexity. This notation gives the tight upper bound of the algorithm. Tight upper bound. Upper bound means maximum time an algorithm can take to execute and maximum space an algorithm can take in the memory. That is upper bound of the algorithm. So this notation gives a tight upper bound of the given function. So generally it is represent as fn of order of gn, order any big O of gn. This means at larger value of n. When we increase the size of n, the upper bound will also increase. This is called your big O notation. Asymptotic means this is notation mainly represents upper bound of algorithm. Formula is your fn is less than equal to c of gn. Fn will be called your big O of gn if, what will the condition? If fn will be your less than equal to c of gn, where c is your constant. C will be always your constant. Fn, these are two functions, fn and gn, and fn will be called your big O of gn if fn will less than equal to c into g of n, where n will be always greater than equal to n naught. N naught will be that value. After that, n always will give the maximum iterations, maximum number of steps, maximum values. And see, these are the constant value. So the definition of big O will be like fn and gn to be non-negative positive functions. These are two functions, fn and gn, and fn is called your order. This is your O, that is your order of g of n. Fn will be order of g of n if there exists two positive constants. What are these constants? C and n naught. Two positive constants, c and n naught, such that fn, this function of fn, that will always be less than equal to c into g of n. C is constant, n naught is also constant, and the value will be n and c always be greater than 0. If this is the condition, this will be the condition, then the complexity will be your big O of gn. Big O, that will be big O of G of n. Fn is called your big O of Gn, where Fn and Gn, these are two functions for two positive integers, C and G, Cn and not, where Fn, the value of Fn always be less than equal to C of G of n. For all positive integers n and C, always be greater than 1. That will be big O. Here you can see that for a given function Gn, we denote order of Gn. It is called your order of Gn such that there exists a positive constant Cn and not such that Fn will be always greater than C of Gn for all the integers, all the value of n that will be greater than n naught. It always describes your upper bound of the algorithm. Upper bound means maximum time it will take to execute to within a constant factor. That is called your upper bound. It always describes your worst case. Always upper bound, maximum time, maximum space an algorithm can take. We can also describe the big O notation with a graph. The graph is shown as, this is your Fn order of Gn. These are the number of inputs. This line shows your number of inputs. This graph describes your Fn, blue line, and this is your C of G of n. N naught is this value. N naught is this value. Until n naught, the value of function Fn that will be fluctuate. The value of Fn will always fluctuate until n naught. After n naught, when I increase the value of input, the function growth will always be greater than your f of n. This graph indicates that the value of f of n of n that will be always less than equal to C dot G of n. It means Fn will be always in the upper bound complexity. For example, there is an example. Here you can see that Fn is 2n plus 3. The value of Fn is 2n plus 3, and the value of Gn, that is your n. Function Fn, that is your 2n plus 3, and Gn is n. Formula is Fn less than equal to C dot Gn, where n always be greater than equal to n naught, where n, the value of n is greater than, after this point, after n naught, we can see that the value of C of Gn, after n naught, we can see that the value of Gn, C of D of Gn, that is greater than your f of n. This point. After the value of n naught, n is always greater than equal to n naught. For all, C will be greater than 0 and n naught will be greater than equal to 1. Yeah, C n naught also will be greater than 0. There you can see that Fn equal to 2n plus 3, Gn equal to n. So now put the value n equal to 1. If I put the value n equal to 1 in the Fn, after calculating, the Fn value is 2 into 1, 1 plus 3, that is equal to 5, and Gn equal to C of n equal to 1, then the C of n equal to 1. So put the value of n equal to 1. Such n equal to 2, then you will put the value 2, 3n plus 2n plus 3, then the value will be 2 into 2, 4, and plus 3, 7, 8 less than. So now you can see that in all the conditions, the value of n after the value of n naught, the maximum amount of time it will take to execute, that will be the worst case. The maximum time it is taking to execute a particular problem. So in general, we see that never consider lower values of n. In all the notations, in all the complexes, in general, we do not consider lower values of n. That means the rate of growth at lower values of n is not important. We always consider the value after n naught. For a smaller range of the number of inputs, we never consider that. We always consider the maximum number of inputs. The rate of growth at lower level of value, that is not important. So n naught is the point from which we consider the rate of growth for a given algorithm. Because below n naught, the rate of growth may be flexible, may be different. For different number of input, the growth will be different. It will fluctuate according to the number of input. So we always analyze the algorithm at larger values of n. This means we don't care about less values, few rates, do not care for rates of growth. That is your big O notation. That will also describe your worst case complexity, maximum time it is taking to execute, upper bound of the algorithm, maximum space and maximum time it is taking to execute. Next is your omega notations. Similar to big O.
Excuse me, sir.
Okay.
Sir, some student asking for joining.
Yeah.
They are waiting.
Admit. Okay, now it is visible. Omega notation. My PPT is visible or not?
Yes, it
Yes,
is
sir.
visible, sir.
Absolutely.
Okay.
Visible, sir.
Okay. Omega notation. As your big O notation always gives your upper bound of the algorithm, the omega notation gives the tighter lower bound. Big O is tighter upper bound, maximum time it is taking, and big omega or big omega, simple omega, that is gives the tighter lower bound of the given algorithm. And we represent it Fn equal to omega of g of n. This sign omega. That means at larger value of n, the tighter lower bound of Fn is g. A tighter lower bound means best defined it Fn equal to omega of g of n. There also exists two positive constants here, gn and naught. Now the condition will be reversed. C of j n will be always greater than equal to n naught. Gn is an asymptotic lower bound for f of n. And g of n, omega of g of n, is a set of functions with smaller or same order of the growth of the function, either smaller or same. In upper bound, it is always bigger, but is omega, it will be always same order or smaller than. One more student is there. From next class, all students kindly join in time. Now it is visible. Omega notation. Okay.
Yes.
Okay. Okay.
Yes.
So it always describes your lower bound of the algorithm runtime. You can see that Fn is now greater than equal to C of Gn. In big O, Fn is always less than equal to C of Gn. But in omega, that is always greater than C of Gn. For n is greater than equal to n naught, where the value of C and n naught is always your greater than 0. Both are constant. It always describes your best case, denotes your best case, lower bound, tightest lower bound of the algorithm. Such as, now you can describe it. Fn is your omega of g of n such that there exists two positive constants c and n naught. The condition will be the value of g of n, that will be your greater than equal to 0 and less than equal to f of n for all the value of n greater than equal to n naught, because until the till the value of n naught, the function value will always fluctuate. After the value of n, after a certain amount of given input, it will always work in your bus case. Okay, so we use omega notation to give an asymptotic lower bound on a function within a constant vector, as we described. This means that there exists some constant c such that Fn is always greater than your c of g. It is also described in terms of your graph. You can see that their time, this is your number of inputs n. You can see that now Fn, the value of Fn is always your greater than c of g of n. In big O, the graph was just reverse. The value of Fn is less than c of gn. But in when the time, when the value of n naught will be increased, when the number of inputs are increased, after point n naught, the value of Fn will be always your greater than c of g of n. Until n naught, it will fluctuate according to the number of inputs. Okay, this is one example, Fn equal to 3n plus 2. Same example, after giving the number of inputs, giving the value of n, you can check that. Okay, next your theta notations. Theta notations always describes your average case of an algorithm. It represents your average bound of algorithm running time. Average amount of time, how much time it will take. Average amount of time, average amount of space. So theta notation is called your average case time complexity of algorithm. Here, the value of Fn will vary between the tightest upper bound and tightest lower bound. You can see that the value of Fn is your greater than c of g of n, and the value is your less than c2 dot g dot n. So it describes between your lower upper bound, your tightest lower bound, and your tightest upper bound. The average bound, it describes your average bound. One is your upper bound, one is your lower bound, and it is between your worst and best case. It is your average bound, average amount of time to execute a algorithm. There you can see that for a given function gn, we denote theta. This symbol is theta, theta of g of n, such that there exists now two positive constants c1 and c2, and one is n naught, such that the value of C of G of n, that will be your 0 greater than equal to 0, and the value of function will be between your worst case and your best case for all the value of n greater than equal to n naught, where C1 and C2 and n naught, these are your constant, and the value of these constant will be greater than 0. So if function fn belongs to the theta of g of n, if there exists two positive constants c1 and c2 such that it varies between, stand between your c1 of g of n and c2 of g n for n greater than equal to n. After some iterations, after some amount of time, it always, the value of f of n will be between worst case and average case. It always describes your average bound. So theta notation describes your average case of your algorithm. The graphical representation of your theta notation is fn equal to theta of g of n. This is your n, size of the input, and this vertical line is your time. Fn function is of n. One is your best case, one is your worst case, and fn varies between those two cases after the value of n naught. Before the value of n naught, it may work differently, but after n naught, the value, the fl will always be between these two cases. This is same example, you can check. Next notation is your little o notation. Generally, we use only three notations, that is your big O, omega, and theta notations. But there are two more notations, that is your little o and little omega notations. Big O describes your tightest upper bound, and little o notation describes your upper bound that cannot be tight. It means the growth rate of fn, function fn, that is slower than gn. It means that is a huge upper bound of fn. Generally, we never use little o and little omega notations. We generally use the big O notations, worst case. When we talk about the algorithm complexity, always we talk about the how much maximum time an algorithm will take. If anyone asking you that what is the complexity of linear search, the answer will be your order of n, because we always talk about the worst case, maximum time an algorithm can take. If anyone is particularly asking for your best case or average case, then you will be able to give the answer about that. Otherwise, you will always give a worst case complexity of any problem. Okay, so little o notation describes your upper bound, not tightest upper bound. It is simply upper bound of the algorithm. Suppose there are two functions fn and gn. For some positive real engineers, real numbers, we can say that function fn is order of gm. It is also called your order of, but it's not big O, it's small o. You can say that is small o. Little o notation. If for any real positive constant c, there exists an integer and not greater than equal to 1, such that fn will be always greater than 0. Mathematically, you can represent it like this. We can say that fn such that n tends to 0, fn of gn equal to 0. So this is, suppose that fn equal to n square, the complexity of first one will be l square and another is n cube. Then check whether fn is order of g of n or not. N square is big O of n cube or not. You can check that. That will be, yeah, n square upon n cube. That will be your 0. So it is n cube. such that little omega, generally we use omega notation for best case. Omega is your tightest lower bound. It is not tightest lower bound. It is little omega notations, small omega. It generally grows Fn faster than Gn, and little o, it grows slower than Gn. In little omega, it grows faster than G of n. There is some example for asymptotic notations, big omega and small omega. Okay, and this is now you are according to your syllabus. Next is your divide and conquer approach. Okay, divide and conquer approach. Actually, this PPT is based on your BTech student syllabus, according to your BTech student syllabus. Next is your divide and conquer approach, which is in your syllabus. In divide and conquer approach, I divide the problem into different subproblems. I will divide the problem into subproblem until it becomes minimum. What do you mean by minimum? Minimum means until we cannot further divide that algorithm. That is called the minimum algorithm in terms of your design and analysis of algorithm. It means the minimal part, the division minimal part will be undividable. I divide the main problem into different subproblems until it becomes minimum. This is called your divide. After dividing the problem, I solve all these subproblems individually. After solving independently, I combine all the solution of subproblems into a solution of whole. So in divide and conquer approach, in this method, a given problem is divided into smaller subproblems. In the first step, it is divided into smaller problems. These problems are called subproblems. In this method, first a given problem is divided into smaller subproblems. Then in second step, these subproblems are solved independently. All the problems are independent, and these subproblems are solved independently. In the second step, after finding out the solution of all the subproblems, I combine all the solutions of subproblems into a complete solution of a particular problem. Then this is called a divide and conquer approach. Divide and conquer. At first you will divide. After dividing, rule, solve the subproblems. After solving these subproblems, conquer all the subproblems. Combine all the solution of the subproblems into a complete solution, into a solution of the whole. So this is called your divide and conquer approach. This is one designing technique. If the subproblems are large enough, then divide and conquer. Then we again apply this technique. Again, this is reapplied. So the generated subproblems is also some time of your original problem. The original problem is further divided. So in divide and conquer strategy, recursive algorithms are used. There is a problem of size n. I'm dividing in equally two parts, subproblem of size n, subproblem of size n. Again further I'm dividing. After dividing, solution of a particular problem, solution of a particular problem. After that I combine all these. Then I will find out the complete solution. So there are some advantages of this divide and conquer. In divide and conquer approach, we have seen that the time it is taking to executing a particular problem in divide and conquer approach, that is smaller than in comparison to other method. In the other method, it is taking maximum time. For example, in searching algorithm, in linear search, the maximum time, the time complexity of the algorithm is your order of n, because it takes your maximum n comparisons to find out a particular problem. But when I use divide and conquer approach in searching technology, in searching techniques, I divide the complete array into two subproblems. Every time I had divided the array into equal to r, in that case, the complexity of that algorithm was log n. So the time spent of executing the problem using divide and conquer is smaller than your other method. So this method is ideally suited for your parallel computation. Why parallel computation? Because I have divided the problem into subproblem, and subproblems are executing parallelly. So this is best ideal for your parallel computation methods. So it is very efficient algorithm in computer science, a divide and conquer approach. For example, there are binary search, your quicksort, merge sort, as we discussed, your instruction matrix multiplications. These are the approach. These are the different algorithms which are based on your divide and conquer rule or algorithm. Because every time I have divided the main problem into some subproblems. For example, I am showing you the working of binary search. Wait a minute. I'm sharing a screen, okay? Wait. Is it visible too?
No, sir.
No, sir.
No, sir.
Then is it visible?
Yes, now it is visible, sir.
Now it's visible, okay. Just the linear search algorithm, okay. Now next I will show you the binary search technique. Here you can see that this is an array where there are the elements 5, 2, 3, 4, 17, and you have to find out the key value, that is your 71. How linear search will work? You can see that. Is it clear in linear search?
Yes, sir.
Now, okay, now
Yes.
you can see binary search. Okay, in binary search, you can see your divide and conquer approach. Is it visible?
Yes, sir.
With the required element given. So today I will be covering binary search, and I am Shreyansh. So before going to the animation, let's first see what is the algorithm. So basically what we do here is we find the middle element and compare with the required element which we need to find. So if the middle is equals to the required element, so we have found the element. But if the middle is less than required element, so we know that required element will be in the right half because the array is sorted. So we will just discard the left part. Similarly, if the middle is greater than the required element, we know required element is in the left half. So we will just discard the right part. So let's see the animation. We have a sorted array and we need to find 8 here. How we will do it? Just that algorithm we discussed, we will apply that. So this is the array with the index mentioned on the top of them. So we will start with 2 pointers. One is at the starting of the array and another is at the end of the array. We will find the middle element index, and that is 4. So our middle element is 7. And 7 is less than 8. So our answer will be in right side and we will discard left side. So we will again do the binary search in the rest part. So these are the pointers which indicates the starting and ending part of the array. We again calculate the middle element, which is the 7th index, that is 12. And 12 is greater than 8. So we will discard the right side. Now again we will do the same operations till we find A. So these are the pointers indicating the starting and ending part of the array. We will find the middle element, which is 5th index, that is 8. And 8 is equals to 8, so we found the element. So this was our binary search algorithm.
Okay. In divide and conquer approach, what I did, I have divided the problem just in equal two halves. Divide the problem into subproblem. After that, I have solved these subproblems individually because all are independent. And after solving these subproblems, I have combined all the solutions. And after combining the solutions, I have found out a complete solution of that problem of that algorithm. Okay, that is your divide and conquer approach. Okay. That is your divide and conquer approach. Okay. Here you can see there, divide and conquer. The subproblems must be solved. Okay, we have already discussed all these things. Next is here. In the mathematical form, if the problem P and the sizes and subproblems will be your N1, N2, and Nk respectively, then the computing time of divide and conquer is described by the recurrence relation. Okay. All the algorithm, the complexity is divided, the complexity is expressed, described in by the different types of recurrence relations. The time complex, the time it is taking. So Tn, total time taking to execute the algorithm of size n, that is your g of n, for n is small, the value of this is your Tn1, the subproblems n1, time taken to solve n1 problem t, time taken to n2 problem plus time taken to n3 problem, time taken to nk problem. N1 problem time, N2 problem time, Nk problem time. This summation is called your T of n, total time taken. Okay, where Tn is the time divide and conquer on any input of size m, for any input. This is total time. This is after division of the time in terms of dividing the inputs. And Gn is the time of compute the answer directly for all the inputs. And Fn is for dividing P and combining all the solutions. I have divided the problems into small problems, and after dividing, I have combined these sub-problem solutions. This total time is your T of n. A general method of divide or conquer. If you have to write an algorithm divide and conquer, then this is divided in small problems, and we have find out the solution for a small problem SP. Else, otherwise, I will again divide that problem into smaller problems. These smaller problems are even P1, P2, Pk until it becomes minimal. It means after division of Pk, the algorithm, the problem cannot be further divided because it is taking your constant time. K is greater than equal to 1 minimum. After this, we cannot divide the problem into further subproblems. And after dividing the problem, I will apply divide and conquer approach, the second and third steps to these subproblems. I will find out the solution of each subproblem, and after that I will combine all the subproblem solutions. You can see that divide and conquer of P1, divide and conquer of P2, and divide and conquer of P of K. There is a complete problem P. I have applied divide and conquer in P, and after using divide and conquer in problem P, I have divided the problem into further P1, P2, P3, Pk. And further I have applied divide and conquer approach in all the subproblems until it becomes your minimum. After that, I have combined all the divide and conquer approaches used in the subproblems. Then I have find out the complete solution of a particular problem P. For example, there is a case Tn equal to 2Tn by 2 plus 1. This recurrence relation is for your merge sort. Okay. The problem n is equally divided into two halves 2Tn by 2. Tn is divided into 2Tn by 2. Every time I have divided the problems into just equal to halves. And Fn is the time that is taking to combine these two subproblems. This is your Fn, as we have told that Fn here. Fn is the time for dividing P and combining the solution of the problems. This is the time. And 2Tn by 2, the problem is divided into just equal to halves n by 2, and n is the time for combining and dividing procedure. Every time after putting the value of n 1, 2, 3, 4, 5, you can see that every time the division is further divided into just two halves, just two halves, just two halves, just two halves, every time. If I'm dividing the problem into just equal to halves, then the maximum height of that tree that is generating after the division of the problem, that will be your log of n, because every time I'm just dividing the problem into just equal to halves, and the maximum time it is taking is maximum time it is taking, that is your n. In solution, it is taking n time, but the height of the tree, that will be your log n, and every time it is taking your n time, and the height of the tree, that will be your log n. The maximum time will be your n into log n. For example, yes, MS. Are you able to see paint page? I'm sharing one paint screen. Okay. In binary search, there is one problem. Is it visible? Paint.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. This is a complete problem. Okay. Then further, I have also divided the problem into equal to halves. Further, I have also divided the problem in equal to halves. Then further, I have also divided the problem in equal to halves. Then further again equal to halves. Okay, and every time combining and dividing, it is taking your n time. Here also n time, here also n time, and here it will also take total n time in divide and conquer approach. In every iteration, it will take your n time, and the maximum height of the tree, that will be your log of n. Okay, the height of the tree is your log n, and every time it is taking your n time, n time, n time, n time, and n time. So the total complexity will be n into log n. So the total complexity will be n into log n. As you can see that 2t n by 2 tn equal to t of n equal to 2t n by 2 plus n. Now it is clear to all? Is it clear?
Yes, sir.
Yes, sir.
Okay, every time it is dividing just two halves and it is taking your order of n time. Further, it is divided into two halves. It is also taking your n time to combine the all solution of all the subproblems and dividing further into
Very small, sorry. The image is so small, sir.
size very small here. Is it visible?
Sir, if you zoom it in, it
Yeah.
will be better.
Now is it clear?
Yes, yes, now it's clear.
Yes, sir.
Yeah, this is a complete problem. Okay. Yeah, this is problem, and further it is divided into just two halves. Further, again two halves. Further, again two halves. And every time it is taking your n time. Here also n time, here also n time, here also n time, and it is also n time in divide and conquer approach, either in combining or in divide approach. The total height and in every step, in every iteration, it is taking n time. So the complexity of this problem will be your n into log. Okay, and the recurrence relation will be your Tn, that is shown in your, that is also shown in here. Here you can see that Tn equal to 2t n by 2 plus n. Every time the main problem is divided into just two equal halves, n by 2, n by 2. And every time, every iteration, it is taking n time. So total height will be your log n, and the total time this problem will take, that will be your order of n log n. So the time complexity of this problem, this is called your order of n log n. Order of means big O of n log n. It means maximum time it will take, that will be your n into log n time. This algorithm will take your n into log n time. That is your tightest upper bound. Okay. The application of this divide and conquer approach is your binary search. Binary search, as we have discussed earlier also. Next is your quick sort. Quick sort is a sorting algorithm. We will also discuss further it. In this algorithm, I have also divide the problem into sub-problem, but not in just equal to halves. We divide the problem according to the pivot value. According to the pivot value, the array is further divided, either left side or right side. We will divide the problem into sub-problems until it becomes your minimal, and then we will combine the solutions. Randomly, we divide the problem into two halves in quick sort. Next is your merge sort. In merge sort, I divide the problem into equal to halves. In quick sort, we use random generator. According to that random generator pivot value, the algorithm is divided. The elements, the problem is divided into two halves. But in merge sort, the array it just equally divides into two halves. After solving, we combine, we merge these two halves and they find out the solution. And this is the recurrence relation of your merge sort. Tn equal to 2t n by 2 plus n. Is it clear to everyone?
Yes, yes.
Is there any confusion?
No, sir.
Okay, I think it's enough for you to revise. Otherwise, it will be very hodgepodge for you. Is it enough for today?
Yes, sir.
Yes, sir. I
Actually,
think
sir.
it's enough for.
Actually, there is a requirement of your board in this subject. This is a purely mathematical subject, but it is very difficult to teach in PPT form. Is it?
Yes, it will be great if you have a Google board or something. Yes,
Yeah, actually, there is a lot
to
of
illustrate things better.
Yeah. Is it clear to all? I think it's enough for today. Okay. We will
We made
meet.
PPT.
Yeah,
Sorry,
this
sir.
this PPT is also shared.
Yes, sir. If you made another PPT and share one day before, we will study that.
Yeah, I will try that. Okay.
Yes, sir.